Welcome back to our quantum mechanics series. In our previous video, we saw how quantum spin measurements give surprising results. But today, we're going to explore something even more mind-blowing: why quantum experiments are fundamentally different from classical experiments, and why measuring a quantum system always changes it forever. Let's start with something familiar: classical physics. Imagine you want to measure the direction of an arrow. How would you do it? You could shine light on the arrow and take a photograph. The light bounces off the arrow, travels to your camera, and creates an image. Here's the beautiful thing about classical measurements: you can make them as gentle as you want. Want to be super careful? Use dimmer light. Worried about disturbing the arrow? Use even weaker light. In classical physics, there's no fundamental limit to how gentle your measurement can be. You can, in principle, measure the arrow's direction with arbitrarily weak light and get an accurate result without significantly affecting the arrow itself. This is what we mean by gentle measurement. The measuring process has a vanishingly small effect on the system being measured. But quantum mechanics throws this gentle approach out the window. Here's the shocking truth: any interaction strong enough to measure some aspect of a quantum system is necessarily strong enough to disrupt some other aspect of the same system. Let me repeat that because it's crucial. You cannot learn anything about a quantum system without changing something else about it. This isn't because our instruments are clumsy or because we haven't figured out better measurement techniques. This is a fundamental law of nature at the quantum scale. Remember our spin measurement experiment? Let's see this principle in action. We start with a spin prepared in the sigma equals +1 state along the z-axis. If we measure it again along the z-axis, we consistently get sigma equals +1. So far, so good. This seems like we're not disturbing anything. But here's where it gets interesting. Between those successive measurements along the z-axis, let's sneak in a measurement along a different direction, say the x-axis. The experiment sequence: 1. Prepare spin with sigma equals +1 along z-axis. 2. Measure along z-axis, get sigma equals +1. 3. Rotate apparatus 90 degrees and measure along x-axis. 4. Rotate apparatus back and measure along z-axis again. What do you think happens in step 4? The shocking result: if measurements were truly gentle, we'd expect to get sigma equals 1 again in step 4, just like in step 2. After all, we just rotated the apparatus back to its original position. But that's not what happens. The intermediate measurement along the x-axis completely randomizes the spin as far as the z-axis measurement is concerned. When we measure along z-axis again, we get a completely random result: 50% chance of +1, 50% chance of -1. The intermediate measurement has destroyed the information about the original z component of the spin. This leads us to one of the most profound insights in quantum mechanics. Measuring one component of a quantum spin destroys the information about other components. You simply cannot simultaneously know the spin components along two different axes in any reproducible way. This isn't a limitation of our technology, it's a fundamental feature of reality at the quantum scale. There's something fundamentally different about the state of a quantum system compared to a classical system. This principle has enormous implications. 1. Information trade-off. Every quantum measurement involves a trade-off. Gaining information about one property means losing information about another. 2. No hidden variables. This rules out the idea that quantum particles have predetermined values for all their properties that we just haven't discovered yet. 3. Quantum uncertainty. The randomness in quantum mechanics isn't due to our ignorance, it's fundamental to nature. 4. Measurement problem. The act of measurement doesn't just reveal quantum properties, it actively participates in creating them. This non-gentle nature of quantum measurement isn't just a theoretical curiosity. Quantum computing, Quantum computers rely on this principle. Measurements collapse quantum superpositions. Quantum cryptography. Eavesdropping on quantum communications inevitably disturbs them, providing perfect security. Fundamental limits. This sets ultimate limits on how precisely we can know certain combinations of quantum properties. What we've learned today reveals the heart of quantum mechanics, the classical idea that objects have well-defined properties independent of measurement simply doesn't apply at the quantum scale. In the quantum world, measurement isn't passive observation, it's active participation in creating reality. Every time we measure a quantum system, we're not just reading its properties, we're fundamentally altering its quantum state. This is why Einstein struggled with quantum mechanics and famously said, "God does not play dice." He couldn't accept that the act of measurement could be so fundamental to the nature of reality itself. But as we've seen, this isn't a flaw in quantum mechanics. It's one of its most profound insights. The universe at its smallest scales operates according to rules that are completely different from our everyday experience. In our next video, we'll explore what this means for the famous observer effect and dive deeper into quantum superposition. Until then, remember, in the quantum world, there's no such thing as innocent observation. Thanks for watching, and don't forget to like and subscribe for more mind-bending quantum physics.